So this section is about inner product spaces or normed spaces. So we thought about vector spaces already. So vectors are objects that can be added to each other or multiplied by scalars. But vector spaces alone are not interesting enough from a statistical point of view until we equip them with a sense of geometry. So we want to know how long a vector is, or the angle between two vectors. And the way we create that geometry is via inner products or norms. Okay, so inner products give us a sense of angle, and they also lead to the sense of distance. They define a norm. Okay? So if V is a vector space, then an inner product is a map from two elements of V to the real numbers. And it obeys a few properties. So the first property is that it is linear in both of its arguments. So if we've got a vector V1 and V2, then if we take alpha times V1 plus beta times V2 and inner product that with U, another vector in our vector space, this is alpha times the inner product of V1 with U plus beta times the inner product of V2 with U. Okay? And similarly, we could have written it's linear in the other argument. So if we wrote U as alpha U1 plus beta U2, okay, we would have a similar expression. That's the first property. It's also symmetric, so we have that the inner product of V and U equals the inner product of U and V. And it is positive definite, which means that the inner product of any vector V with itself is bigger than or equal to 0. Okay? And it if it equals 0, so if the inner product of V and with itself equals 0, this implies that V is 0. Okay, so that's the idea of an inner product. An inner product space is a vector space with an inner product. So we often write it as V for the inner product. So inner products equip us with two important concepts. The first concept is that of distance. So an inner product defines a norm. Okay, so let's say let the norm of some vector V be the inner product of V with itself. And we think of the norm of V, so these are vectors, as the length of V. The second concept is that of angle. So if we've got U and V in the vector space V, then so the angle between U and V is theta, where we have that the inner product with U and V is the length of U times the length of V times cos theta. So that defines the angle theta. And in particular, we'll be interested in orthogonal vectors. So we say U and V are orthogonal if theta is 90 degrees, or is pi by 2, let's do it in radians, okay? Which is the case if the inner product of U and V is 0. So the concept of orthogonality is going to be important throughout the module. So pretty much exclusively in this module we'll be working with Euclidean vector spaces. which we can think of as R to n for some n. So just vectors of length n. And in that case, we use Euclidean inner product. The inner product between u and v, which is just u transpose times v. So the norm of u is the square root of the inner product of u with itself, which is the square root of the sum of the individual elements of u, so ui say, squared, all square rooted. Okay, so this is the usual Euclidean definition of the length of a vector. And for that reason, and for reasons we'll see later, we often, when we're using Euclidean inner product, the norm often gets a 2. So this is called an LP norm, which we'll see more about in a moment. The angle here, well, if we think about our rule, we've got u transposed v is the length of u times the length of v cos theta. And you'll recognise as the scalar product rule. Yeah, so u transpose v is sometimes called the dot or scalar product of u and v. So let's make this really concrete. Let's have u be the vector 1, 2, and v be the vector -2, 1. Then the length of u is the square root of u transpose u, so that's 1 squared plus 2 squared, so that's the square root of 5. Okay. Similarly, the length of v is also root 5. And if we think about the inner product between u and v, product between u and v, well, that is u transpose times v, so that is the vector 1, the row vector 1, 2 times the column vector -2, 1, so that is 0. So u and v are orthogonal, which I might sometimes write like this. So u and v are orthogonal. Just finally, I mentioned that this is the 2 norm, the L. This is sometimes called the L2 norm or the Euclidean norm. But there's a whole family of LP norms. So for any positive p, the LP norm of some vector v is defined to be the sum of the individual elements of v, the absolute value of them, raised to some power p, all then raised to the power 1 over p, so the pth root. And you'll see that if we put p equals 2, we get back to the LP norm here. From W to U.